Hello everyone. So in the last video we discussed about dimensional analysis, especially the applications of dimensional analysis. Am I correct? So we discussed about that how to convert any physical quantity from one system of unit to another system. So that is what we discussed in the last class. So as a part of the application of dimensional analysis, today we are going to see the second use of the dimension analysis. So the second use or the second application of dimension analysis is it is used to check the dimensional consistency of the equation, right? It is used to check the dimensional consistency of an equation, right? So this is the second application or the second use of the dimension analysis. So let me explain the topic first of all. You know the meaning of all the words used to check the dimensional consistency of the equation. What is meant by this consistency? Consistency is nothing but it is used to check the correctness of the equation, right? Whether the equation is correct or not. That we can check using the dimensional method. For example, when we started deriving a new equation, okay, imagine that we are deriving a new equation, a new set of equations like a kinematic equations, right? So when we deriving a new set of equations, initially we don't know whether the equation is correct or not. So how to check the correctness of the equation, that consistency of the equation? We can use the dimensional method. So the first step is we can use the dimensional method. Based on the dimensional method, we can check whether the equation is wrong or correct, right? So this is the basic idea or the objective of today's topic. So let's see what is the basic concept behind this, right? Or the basic idea behind this application is, it is nothing but only as physical quantity which is having the same dimensions can be added or subtracted. Let me explain this. For example, I am measuring a length of a body is some 2 meter, okay? A length of a body is 2 meter and the mass of the body is some 1 kilogram. You know both are different quantities. Am I correct? Length and mass are the different physical quantities and they are having the different dimensions, correct? This is having the dimensions L, this is having the dimensions M. All the other dimensions are 0, okay, right? Okay. So now, can I add this length and mass? See, both are the physical quantity of the same body only, right? Can I add the length and the mass? No, right? Why? Because these are the different physical quantities. So I cannot add length and mass. So this is wrong. I can multiply length and mass. I can multiply and I can divide different physical quantities, but I cannot add the different physical quantities, and also I cannot subtract the different physical quantities. Similarly, a physical quantities which is having the same dimensions only can be added or subtracted, right? Only length can be added with length and mass can be added with mass, force can be added with force. We cannot add force with velocity. We cannot add velocity with any other physical quantity like length or distance or whatever, right? So the basic idea is, just write down this, only physical quantities having the same dimensions can be added or subtracted. So this is a very basic idea behind this application. So we are going to use this idea in the application, right? Okay, so only the physical quantity which is having the same dimensions can be added or subtracted. Length can be added with length, mass can be added with mass, force can be added with force, and temperature can be added with temperature, current can be added with current. But we cannot add current with temperature. We cannot add force with area. We cannot add mass with current, right? So different physical quantities or the physical quantities which is having the different dimensions cannot be added or subtracted. So this is the basic idea. Now, so in the last application, we did see a general method or general derivation we did see. Am I correct? We have seen a general method to derive an equation, and the formula based on that we did see how to convert the physical quantity from one system of unit to another system. Am I correct? But here we don't have any derivations on that, right? But here we have a principle. Okay, the last application we had a derivation and we had a equation, but here we had a principle. So based on this principle, we are going to check whether the equation is dimensionally correct or not. Okay, once again I tell you the objective of this method or this application. It is used to check the correctness of the equation. So it is used to check whether the equation is dimensionally correct or not. Dimensionally correct or not. Okay, this is very, very important. This is the key word. Okay, we are going to check the equation dimensionally correct or not. I will tell you the importance of this word at the end of this class. Just remember, we are going to check the equation is dimensionally correct or not, right? Okay, now, so let's come back. So now I am going to tell you the principle that we are going to use for this application, right? The principle is known as principle of homogeneity of dimension. Principle of homogeneity of dimensions. Write down this. The name of the principle is known as principle of homogeneity of dimensions, right? Let me explain what is the principle is. What is mean by homogeneity? You know the meaning. Homo means it's the same kind, everything is same, right? So what is mean by homogeneity? Homogeneity means all of them are same kind, right? All of them are same kind, so that is what mean by homogeneity, right? Okay, now, so now what purpose we are going to use this principle? We are going to use this principle to check whether the equation is correct or not. Am I correct? We are going to check whether the equation is dimensionally correct or not. So you know, in every equations there will be two things. One is the LHS part and another one is the RHS part. Am I correct? Every equation have a left hand side and right hand side. It's like this: F is equal to MA or V is equal to U plus AT. Right? So like this, every equations are having LHS part and the RHS part, right hand side part, right? So what we are going to do here is, we are going to check, that means if both the sides, both LHS and the RHS of the equations having the same dimensions. You know the meaning of the word homogeneity. Homogeneity means all of them are same kind, right? All of them are same kind. So which should be same kind? Both the sides of the equations must have the same dimension. I repeat again, both the sides of the equation must have the same dimensions, right? If it is have the same dimension, then the equation is dimensionally correct. So this is the principle, right? So both LHS and RHS, both the sides should have the same dimensions. If it have the same dimension, then we can conclude the equation is dimensionally correct. So now, so this is the concept or the explanation for the principle. Now I'm going to tell you the exact principle in exact words. Just write down the principle. According to this principle, a physical quantity, a physical equation will be dimensionally correct when a physical equation will be dimensionally correct. When it will be correct? If both the sides of the equations are having the same dimension. Am I correct? So a physical equation will be dimensionally correct if the dimensions of all the term occurring on both the sides of equation are same. That's it. So I repeat once again, according to this principle, a physical equation will be dimensionally correct. When it will be correct? If the dimensions of all the term occurring on both the sides. Because in LHS, we have one term V. In RHS, we maybe have more than one term, right? I'm having U, A and T. Right? So all the terms occurring on both the sides of equations should be same. Okay, when they are same, then the equation is dimensionally correct. So LHS la irukra dimension RHS la irukra dimensions ஒரே மாதிரி இருக்கும். Right? So if L naka, both the sides should have the dimension L. If it is M, then both the sides should have the dimension F. If it is M, L, T, all the powers are 1, then both the sides should have the same dimensions. So that is the concept. This is known as principle of homogeneity of dimension. So இதை பேஸ் பண்ணி தான் we are going to check whether the equation is dimensionally correct or not. So இதில் derivationsலாம் எதுவும் கிடையாது, just the principle. So now we will see one example. Okay, so this is the principle. So we will see one example. Okay, let's check the dimensional accuracy of the equation of motion. S is equal to ut. You know the kinematic equations, right? So the second kinematic equation, S is equal to ut plus of at square. So now I am going to check whether this kinematic equation of motion is dimensionally correct or not. That's what I am going to check, right? So what is the first thing we have to do? You know the concept, what we have to do, how to check the correctness. Both the sides should have the same dimension. Am I correct? Both LHS and RHS should have the same dimension. So what I have to do, I have to write all the terms in the dimensional formula. Okay, I have to write the dimension formula. So just write it. So what is S? S is nothing but it is the distance, position, displacement. So what is the dimension of S? It is L. Now come to U and T. What is U? U is the velocity. So it is like distance by time. So it is LT power minus 1. So this is the dimension of U. And then T, this is the dimension of T. Plus of, what is 1 by 2? 1 by 2 is a constant. Is this constant have any dimension? No, right? This is dimensionless constant, right? This is dimensionless constant. So it does not have any dimension. So I don't need to put any dimensions, right? So we just neglect it. We can directly go to the AT square. What is A? It is acceleration. So what is the dimension? LT power minus 2, then T square. So this is the dimension. So the first step is write the dimensions of each term on both the sides. So dimensional formula எழுதும். Okay, next step என்ன, right? We are going to solve the equation. You know this is T power minus 1, this is T power 1. It is in multiplication. So multiplication we can do anything, right? It is T power minus 1, it is just T, so both will cancel. So I'll have only L. Am I correct? Now plus L T power minus 2 and T power 2. So this is, I can cancel. So again, yeah. Now you can see this is left hand side and this is the right hand side, which means both the sides of the equations are having the dimension. What dimension? LHS having the dimension of length and RHS is also having the dimension of length. So which means both the sides are having the same dimension. So that's why we can confirm or we can say the equation is dimensionally correct. Am I correct? See, if you add this, what will happen? You know, the basic idea is we can add the same dimension. So even if I add the number, even if I add this dimension, I will get 2L only. What is 2? 2 is dimensionless constant. So it is nothing but L is equal to L. Okay. So இதோடவே நம்ம நிறுத்திடலாம். We can just stop at this step itself. Okay. So you can put any number of L's. எவ்வளோ n number of L's போட்டாலும் it is in addition. Okay. எத்தனை number of L's இருக்கு அப்படின்றது முக்கியம் கிடையாது. Whether both the sides are having the same dimensions. LHS ல என்ன dimension இருக்கோ அதே தான் RHS லயும் இருக்கணும். பட் அது எத்தனை முறை வேணாலும் இருந்திருக்கலாம். அத பத்தி பிரச்சனை இல்லை, right? So now both the sides are having the same dimensions, so that now therefore since the dimensions of all the terms here, you know this is S. So S term is having the dimension L, and here you can see ut plus of at square. Even all these terms are having the dimensions L. So what I can conclude, I can conclude like this: since the dimensions of all the terms are same, therefore the equation is dimensionally correct. The equation is dimensionally correct. That's it. I again giving more importance to this word. The equation is dimensionally correct. Why I should give more importance to this word? Let's see. And very, very important thing that we have to note here is, it's a very important point. Just listen here. You know the equation is S is equal to ut plus of at square. Now I check, based on the dimension analysis method, I check this equation is correct. Okay. Now instead of writing the equation like this, if I write the equation like this, ut plus 1 by 4 at square. Instead of writing of at square, I am writing 1 by 4 at square. Okay. So I am just deriving the equation newly. இப்பதான் நான் புதுசா அந்த equation derive பண்றேன். நான் derive பண்றப்ப I am getting the equation like this, 1 by 4 at square எனக்கு கிடைக்குது. Now I am going to check whether it is correct or not. What do you think? whether I will get the same dimensions of on both the sides? Yes, because 1 by 4 is dimensionless constant. So இப்போ இந்த 1 by 2 இருக்கிற இடத்துல நான் 1 by 4 போட்டாலும் சரி 1 by 6 போட்டாலும் சரி 20 200 30 எந்த நம்பர் போட்டாலுமே it does not going to affect the result because it does not have any dimensions. Am I correct? So even if you derive for this equation, again you will get the same dimension on both the sides. Okay, so what I can see from here, actually 1 by 2 இருக்கிற இடத்துல 1 by 4 னு போட்டா equation தப்பு தான். You will get the wrong answer only. The equation is wrong only, but it is dimensionally correct. Am I correct? Right? I repeat once again. Here in the place of dimensionless constant இருக்கிற இடத்துல if I put any other constant, it does not going to affect the result because it is dimensionless. So that's why it is does not going to affect the result. So I will be having the same dimension on both the sides. So இப்போ செக் பண்றப்ப எனக்கு என்ன ரிசல்ட் வரும்? The equation is correct அப்படினா எனக்கு ரிசல்ட் வரும். Okay, so இப்போ நம்ம என்ன இதுல இருந்து கன்க்ளூட் பண்ணலாம் அப்படினாக்கா, now you can see this equation is dimensionally correct. Am I correct? Even this equation 1 by 4 80 square is, it is dimensionally correct but not an actual equation. Am I correct? This is not the actual equation. Okay, so இப்போ dimension method யூஸ் பண்ணி நம்ம என்ன கண்டுபிடிக்கலாம் அப்படினாக்கா, we can just check whether the equation is dimensionally correct or not. அதை மட்டும் தான் கண்டுபிடிக்க முடியும். But we cannot say that is the actual equation, right? So the equation இதுதான் கரெக்டான equation, we can't say 100% surely, right? But the only thing we can do is we can check whether it is dimensionally correct or not. So just write down the note. The very important note we can understand from this point is, so now you can understand why I am giving more important to this word dimensionally correct. You can't simply write the equation is correct. Equation correct nu eludukudadu. We have to write it is dimensionally correct. Okay, right. Now you understood why I am giving more important to that word dimensionally correct. No. So now the important conclusion from this explanation is, in the method use panni, okay, using this dimensional method, when I am checking this correctness of the equation, when I am checking the equation, இப்போ என்ன பண்ணலாம் அப்படின்னாக்கா, if I am getting the result correctly, for example ரெண்டு சைடும் எனக்கு சேம் டைமென்ஷன்ஸ் வந்துருச்சுன்னா நான் என்ன சொல்லலாம், அது கரெக்ட்னு சொல்ல முடியாது. Am I correct? I can't say it is 100% correct. In case if the dimension itself is not same, here it is L, here it is some M and then L, now it is not dimensionally correct. Am I correct? If the equation, if the result is like this, LH is having the dimension of length, but RH is having the dimension of M and also the length. So now the equation is not dimensionally correct. So dimensionally correct illada ஒரு equation actually correct இருக்காது. Am I correct? So இந்த மெத்தட் வந்து பாஸ் பண்ணாத எந்த ஈக்குவேஷனுமே நிச்சயமா கரெக்டா இருக்கிறதுக்கான வாய்ப்பே இருக்க முடியாது. Understood? Okay, so the first thing we have to understood from here is, if any equation, if an equation fails this test, so this is the first step of analyzing. This is the first test. ஒரு ஈக்குவேஷன் புதுசா கண்டுபிடிக்கிறப்ப இந்த டெஸ்ட் தான் ஃபர்ஸ்ட் பண்ணுவோம். we are going to use the dimension method. so அந்த டெஸ்ட்ல நமக்கு கரெக்டான ஆன்சர் வரல, if the both the sides are thus not having the same dimension, அப்ப என்ன கன்க்ளூட் பண்ணிரலாம், நம்ம கண்டுபிடிச்சிக்கிற ஈக்குவேஷன் 100% wrong னு கன்க்ளூட் பண்ணிரலாம். Okay, if the equation fails this test, then it is proved. If the equation fails this test, it is proved wrong. 100% surely we can prove the equation is wrong. Eppo, when both the sides are thus not having the same dimension. So இப்போ இந்த மெத்தடை, இந்த டெஸ்ட்டை பாஸ் பண்ணாத எந்த ஈக்குவேஷனுமே கரெக்டா இருக்கிறதுக்கு வாய்ப்பே கிடையாது. it is 100% wrong. We can prove it is wrong. So இப்போ ஒரு ஈக்குவேஷன் wrongனு prove பண்றதுக்கு we can use this. But if the equation pass this test, if the equation passes this test, we can't make sure, that means we can't say the equation is 100% correct. அது ஆக்சுவலான ஈக்குவேஷன் சொல்ல முடியாது. it is just dimensionally correct. Okay, so if the equation passes this test, not prove, it does not prove it is correct, 100% correct or the actual equation. So இது pass பண்ணிச்சு அப்படினாக்கா it is just dimensionally correct. Okay, if it is pass this test, it is just dimensionally correct. That's it. In case if the equation fails this test, then we can 100% surely say then the equation is wrong. So the conclusion from this is, if dimensionally correct equation, I repeat again, a dimensionally correct equation need not be an actual equation. Am I correct? Dimensionally correct your equation actual equation need not be an actual equation. Right. Okay. Like how we proved here, S is equal to ut plus 1 by 4 at square. This equation is dimensionally correct. Even though it is dimensionally correct, it is not the correct equation. It is not the actual equation. So what we can conclude, a dimensionally correct equation need not be an actual equation. But dimensionally incorrect equation, dimensionally inconsistent or incorrect, whatever, dimensionally inconsistent equation or dimensionally incorrect equation must be what? It must be wrong. So just write it down. So this is the main conclusion that we can, main important thing that we have to note, right? So இப்போ இந்த டெஸ்ட் யூஸ் பண்ணி நம்ம ஒரு ஈக்குவேஷன் தப்புன்னு ப்ரூவ் பண்ணலாம், சரின்னு ப்ரூவ் பண்ண முடியாது. Am I correct? So using this method, using the dimension method, we can prove the equation is wrong, but we can't prove the equation is correct. So if the equation is dimensionally correct, then it does not need to be an exact equation. So the next step க்கு proceed பண்றதுக்கு we can have a hope. Maybe அது கரெக்டா இருக்கிறதுக்கான சான்சஸ் இருக்கு. But if the equation is dimensionally incorrect, இந்த மெத்தட்லயே அந்த equation வந்து இந்த டெஸ்ட்டை பாஸ் பண்ணல அப்படின்னாக்கா, then the equation must be wrong. So this is the first step to check whether the equation is correct or not. Okay, so like this only we are going to check whether the equation is dimensionally correct or not. Okay, so what is the basic concept? It's a very easy. It is the principle of homogeneity of dimensions. So we are just going to use the principle of homogeneity of dimensions. So both the sides should have the same dimension. Equation இருக்கிற each and every term in LHS and RHS, both the sides should have the same dimension. So அப்படி இருந்துச்சுனாக்கா we can say the equation is dimensionally correct. So right, so this is the concept. So now this topic is over. Now I'm going to give you a few homework sums. Just wrote down the sums. Okay, so these are the practice problems. You can practice these sums using the same method of mv square is equal to mgh. The second one is E is equal to mc square. So all these are equations. T is equal to 2 pi root L by G. So this is L, root L by G. So these are the worked out problems. So you can just practice these problems. So you can see all these are equations having LHS and RHS. So what we are going to do, we are just going to write the dimension formulas. So at the end, if you are getting the same dimensions on both the sides, then we can say the equation is dimensionally correct. Okay, but it doesn't mean it must be the exact equation, right? All right, so thank you.